Okay, so let's look at question 5. First of all, could you cub the question, please? Okay, so let's see. Okay, so this is a big question. It's worth 5 marks in total. You can see down here in the bottom right corner, 5 marks. I've got to use results as well from the graph. Okay, in my explanation. So there's 2 command words. One is I've got to describe the motion, and the other is I've got to use results from the graph in my explanation. And it's worth 5 marks in total. So a really big question is, so first thing is I'm going to write my 5 bullet points out. So 1, 2, 3, 4, 5, and I'm going to have to describe what's going on in this graph. Now, just looking at the graph, it's a complex graph. There's lots going on. It's not a simple straight line, or I can see it's going up, but it doesn't do that, it doesn't do that, it doesn't do that. And the fact it's 5 marks suggests it's going to be more complex than that anyway. So these are the 3 basic shapes, I guess, for any graph going that increases. And there's multiple types of those shapes in here. So I'm just going to quickly have a look at what shapes I can see. Well, first of all, I can see a straight line at the top there. So let me just put that in. Normally in the exam you'd actually be given the line itself, because you wouldn't have to do this as a line of best fit because it's far too complex. Distance time graphs or velocity time graphs are pretty much the only graphs you're likely to see frequently anyway in science that do dot to dot. So this graph would look something like this. Okay, so that's the shape of the graph. Now you can see it's a bizarre shape. Worth 5 marks. I need to describe what's going on, describe the motion. So the first thing I'm going to do is I'm going to section my graph up into bits. So the first section is here. So when I say section, I'm just chopping it up into bits that I can talk about each bit more easily. So there's one bit, here's another bit, and then the final one is over here. Okay, and I'm just going to, because I've got to use results, I've got to use data, and I'll just put down, right, what's that there? That's 1. This here is going to be, so that'll be 5. What's this going to be? So there's 1, 2, 3, 4, 5 squares for 5x. So I'm going to write x rather than s because my s's look like 5s. So 5x, with each x is a box. But let's do b. So 5b for box equals 2 squares, equals 2 in total. So one box is 2 divided by 5. 2 divided by 5 is, and I'm going to use my calculator to make sure I get it right, 2 divided by 5 equals 0.4. So each box is worth 0.4. So this is a box and a bit. Just going to work out roughly how much of that. Well, that looks like it's about a quarter of that box there. So each box is 0.4. So that's going to be 4.4 to here plus quarter of a box. So that's going to be about 4.5 total there, and obviously that's still 10. That's an easy one. So these are the values I'm going to use when I'm explaining what's going on, because I've got from 0 to 1, it goes from 0 up to 10. So I'm going to use that number. Now I'm going to use this number here, which is 1, 2, 3, 4, 5. So each one of those is 1, so 21, 22, 23, 24, 25, so that's 24, so I'm going to talk about that as well. Okay, because the reason I got the 24 there is because, let's just draw that across just so you can see where that's from. That's from there, 10 was from there. Okay, so that's the points I'm going to talk about. So let's see how we do this. So that's there. So the first one would be for time 0 to 1 minute. Okay, so I'm talking only worrying about this first little section here. For time 0 to 1 minute, what happens as time increases, distance increases at a constant, sorry, not at a, with a constant steepness or rate from 0 meters to 10 meters. I've used lots of data there. I've used my perfect conclusion for that first part. Right, I'm going to then talk about the next bit. So for time, I'm going to start from this bit, from 1 to 4.5. For time 1 to 4.5 minutes. What's going on there? As time increases, distance increases. Okay, and for the second part of my perfect conclusion, with, and what's going on here with the slope. So if I imagine I'm walking up that, I'm looking that way there. Okay, this hill is getting steeper and steeper. Okay, it's much steeper here. So the steepness is increasing with an increasing steepness or rate. And I might choose there as well, just to put some values from 10 to 24 meters. Okay, just to make sure I get the mark for using data. And the very last bit is this bit here, the horizontal bit. So all I've got to do is talk about that, and that's from 4.5 to 10. Now you might get a little bit bored. You think each sentence looks a bit, or each sort of double sentence looks quite similar, it's repeating, but that's fine. We've got a method that works, so we're just going to keep using it. So for time 4.5 to 10 minutes, distance stays constant. Distance stays constant, and I'm going to say what it at 24 meters. 24 meters. Okay, so that would easily get all 5 marks, potentially 6 marks if it was a 6-mark question, because I've used lots of data. So I'll get 1 mark for using data. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 pieces of data in there in total. It might seem like I've written quite a lot, but actually it's a 5-mark question, which is over a grade. Remember, it's worth it. You know, it's worth an awful lot. I haven't really taken that long. You'd have much more room to write this. You'd probably get 2 or 3 lines per mark. But all I've done is I've reused that same simple conclusion, the perfect conclusion. As x increases, y increases or stays constant at with what sort of steepness, what's happening to steepness. And I've made sure I use that word rate every time. Okay, if I've really revised this hard and I know actually the rate of change of distance we call velocity, that's fine, but rate is also totally appropriate. So if I just remember rate because that's correct, it's a much easier term to remember, and I can apply it to any graph or any sort of different scale that we might have. Okay, next question.